It's a wonderful opportunity to be here, and coming back to Canada again is wonderful. You can see from this. Oh, I can't point. I wondered if we're actually the opposite parts of the Earth, but it's a little bit off. Obviously, you know where your antipode is, and so I'm somewhere down there. Somewhere is where I come from. What I'm going to talk about is the quantum theory of time. It's my theory. I have to be quite courageous to present this work. It's stuff I've been working on for about 10 years. I've only published 3 papers on it. Doing other work at the same time. It's controversial, but it's very fundamental. So you might think about time, the direction of time, and this is a big issue in physics about why are we seemingly moving towards the future. Philosophers have a lot to say about there is no flow of time. We have this model you might have heard of it, the block universe, where there is no time. It's a 4-dimensional space-time block. And there's no present, although I feel like I'm standing here before you, but the objective view of this is that there is no flow. And what people tend to do is they look to thermodynamics to give us, these things that are called arrows of time for explaining the direction. Now, if you look at this slide, see what I've got here is an analogy, if I got the button. Imagine there's a tree and there's some wind blowing, and the wind blows the leaves on one side of the tree. Now what you would say is the pattern of the leaves on one side of the tree would tell you that the direction that the wind is blowing. But the pattern of the leaves doesn't make the wind blow. And what people do with entropy, associating the increase in entropy, the thermodynamic arrow, they think that it sort of creates time. It creates the dynamical nature of time. But it's just evidence. So an increase in entropy is just evidence that there's something dynamic going on, but it doesn't create it. Okay? So it's really kind of dead. I mean, thinking about an entropy increase is really going to tell us nothing about the nature of time at all. And that's probably the most controversial thing I can say, because so many people are convinced that the entropy is what you need to really focus on. I published a paper last January and it kind of went viral, which I'm really happy to say. So that's the reference, quantum asymmetry between space and time. What I was interested in is that from relativity, we like to think of space and time being interconvertible, but there's something that really makes them different, and that's dynamics. I'll talk more about this later. And I wanted to see why we have that difference. Well, I published that paper last year. Reddit, I don't know if you look at Reddit, but it was voted 5,000, so there was a lot of discussion there. I didn't reply to anything, but people were really getting into it and trying to understand it, which I thought was really, really nice. So it has had 50,000 reads, 8,000 downloads, and New Scientist voted it as one of the best 5 theories of time. So, I mean, at least I've got a fan and New Scientist. I think it's the best theory because the other theories were very sort of old, been around for some time, things to do with entropy, where does the low entropy state come from and things like that. They don't really solve an anomaly though. They're just other ways of trying to make a more satisfactory approach to time or thinking about time in a more satisfactory way. What I'm doing is actually solving an anomaly. So you have to identify these things. So my message today to young people is to always look for these anomalies. If you come across one, it's going to be, it's very difficult to go through and solve them. I mean, there's huge anomalies, aren't there? There's the dark energy. We don't even know it's dark energy. Chandra gave us a wonderful talk just before. The dark matter problem, that's an anomaly. We solve these anomalies by changing our paradigm. Einstein solved an anomaly to do with the speed of light, constant speed of light, and so on. There's it's not so much anomalies, but incompleteness, like the quantization of gravity. But there's so many people working on these things, you have to be really clever to compete. The best anomalies are the ones that people don't even know that they're anomalies. And if you're clever enough to find them, then that's the thing to go for. And what I've always done, right from my student days, is, you know how the best way to study is not to look at the answers, to work things out for yourself. Well, I've done that all the way through. If I see a paper, I try and work it out before I read what the authors have done and things like that. So I've really tried to keep this, I don't know what you would call it, about some sort of creative process of thinking, trying to solve things. It all comes down to T violation, and Chandra mentioned the kaon and anti-kaon and problem before. This is CP violation. Related to CP violation is T violation. So T violation is the violation of time reversal symmetry. All our laws are time reversible. They give exactly the same dynamics in both directions. But these kaons and B mesons exhibit dynamics which is not time reversible. So this is quite different from entropy. Entropy is not the kind of thing. Entropy, you can have entropy increase with time symmetric laws. It's really about boundary conditions. But here, it's really about dynamics. So if you look at, and this particular experiment, there's lots of different experiments, but we have an anti B meson, neutral B meson, evolving into a minor superposition of a B meson and its anti-particle, the anti-B, because this is a superposition of the two. And this other experiment here is looking at that superposition changing into a B, the anti-B. And they take different times. And this is evidence that there's two Hamiltonians, one for a forwards direction in time and one for the reverse. This is the time. I'll talk more about the time reversal operation here. There are two Hamiltonians. The problem is so T violation tells us there are two Hamiltonians, two versions of the Hamiltonian, but all our physical theories only have one Hamiltonian, if they've got a Hamiltonian formalism, or there's only one dynamics. They only produce or model one set of dynamics, but there should be two. So this is an anomaly. Most people don't like to talk about it. There's all these ways of talking about T violation and dismissing it as something that happens in little particles, can't affect us on a large scale. But when you think about time, looking at things like entropy, which is the standard way of looking at these things, is talking about using time-symmetric laws with time asymmetric boundary conditions. And asymmetric boundary conditions is things like, low entropy to begin with and large entropy later on. And asymmetric boundary conditions won't help us understand what time is. They're just very easy to talk about. But if you've got a time asymmetric dynamical law, that's going to tell you something about time. And it's just been really dismissed and not really looked at. So I was asked to write a paper for a book, a chapter for a book, and this really discusses the anomaly. I highlight what the anomaly is. So there's a link. It's open access, and you can easily download it. So it's written for the non-physicist. So the idea, if I just go back to this slide here, so if we've got two Hamiltonians, if we're going to develop a theory to include two Hamiltonians, and there's two sets of dynamics associated with those Hamiltonians, then maybe we need to rethink what dynamics is. So that's my approach, is to rethink dynamics. And we might need to throw some things away and justify them, later on. So to rethink dynamics, well, from special relativity that space and time are somehow interconvertible. The minus sign, which tells us, we treat space a little bit different from time, it's not really saying that they're different. It's really a speed limit or a ratio between the two. So apart from that speed limit, space and time can, take on, it's interconvertible. The dynamics, however, if you look at dynamics, they're what dynamics are, it's about evolution over time. So you can have things that are localized in space, but because of dynamics, they can't be localized in time. For example, you can have a particle that's got a wave function in space, that's fine, it doesn't exist over here or there, and you can normalize that wave function. But over time, you can't have a wave function like this, that there's no particle here, there's a particle here, but there's no particle there. Okay, so this is the idea of localizing in space, but not localizing in time. And that's because we have dynamics that carries particles all through time, and conservation laws, that's what a conservation law is. It's telling us about dynamics. It's a quality of dynamics, a symmetry of dynamics. But if we really want to stick to this idea that space and time are interconvertible, then shouldn't we be able to have this? That shouldn't particles be able to be localized in time? Well, that means we have to give up conservation laws. We have to give up equations of motion and conservation laws. So I want to tell you how to be so courageous to do that. So when I started this work, I sort of felt like, well, I don't think I could call myself a physicist for a while. I'll just put that aside. If I'm putting aside conservation laws and dynamical equations of motion, then it's not really physics in the way that we think of it. So this is the idea. We have, at a fundamental level, this is how particles should be. They should come into existence and disappear, in a sense, in time. So they're not conserved, and so they can be localized in both space and time. And what we want is something else to take us, some phenomena to give us what we see. So this is what we normally see. If you have a particle that's located at a position, it'll be located somewhere else, maybe it's the same position, but it'll be located in time. And it's conservation of mass that keeps this wave function going through time. And so so this is what we want, some phenomenon to give us this. So we want it to emerge. We want this at a basic structure. So normally what we do is that when we have a theory, we assume that there's an equation of motion and then there's conservation laws. They don't emerge. They're assumptions. They're axiomatic. What I'm saying here is that I don't want them to be axiomatic. I want them to come from somewhere. And I think this should help us understand what time is. Now, if you look at the generators of translations in time and space, what you notice is that generators of translations in space, well, that's just the momentum operator. It generates translations in space. The generator of translations in time is the Hamiltonian. Now, these are very different generators. These discrete symmetries like charge, parity, and time, charge conjugation, parity, inversion, and time reversal, those discrete symmetries are violated by the Hamiltonian only. So there's something really interesting about this generator of translations for time that you don't have for generators of translations over space. Okay, so we can get that to work, or hopefully we can get these symmetry violations for these generators to give us this phenomenological emergence of dynamics and conservation laws. So that's what I've tried. So this is the idea. If you look at generators of a translation in space, here's the momentum operator. If you want to do the translation in the opposite direction with a minus sign here, one way to do it is to, well, if this is a translation in that direction, but we want to go in this direction, well, you can do a parity inversion, a translation in the same direction, the positive direction, and then a parity inversion, and that gives you the opposite direction. And that's what this combination here is, okay? It's just a translation in the opposite direction. And the same thing for time. In time, we have to be prepared that we've got two Hamiltonians. Here's one, and I've got it like forwards direction. That's the one that we measure in experiments. And then there's this backward one, which is the time reversed one. So here's the equation, the unitary time operator translating a wave function forward in time. To do the translation in reverse, backwards in time, we would have this operator, the other Hamiltonian.